Yeah.
Good morning.
Okay,
my name
please.
is Jean-Paul Garbeza. This is Alejandro Infante,
Please,
Ricardo
please,
Lopez,
please. Thank you.
and Hector Di Donato. We have been working with the Air Force Research Laboratory for the past 8 months and designing this striking mechanism for our split Hopkinson pressure bar. This is a typical diagram of a hoppy bar, as they're called, and it is composed of two main systems, the stress-inducing system and the stress-determining system. Now, the stress-inducing system is comprised of a striker bar, an incident bar, and a transmitted bar. Now, we take a specimen that we would like to test, and we sandwich it in between the incident bar and the transmitted bar. Subsequently, our compressed gas gun sets our striker bar in motion, and upon impact of the striker bar with the incident bar, we produce a one-dimensional stress wave propagation through our system. The stress-determining system uses strain gauges to measure the amplitude and the stress pulse length of that one-dimensional stress wave. Now, these hoppy bars allow for material characterization at high strain rates. Now, what this means is that generally in textbooks, what we see is quasi-static loading. You grab a material and you apply a load very, very slowly until you reach its breaking points. Now, if we were to grab a hammer and smash that same object, those mechanical properties would react in a different manner. The properties that we are interested in are such as yield point and ultimate stress, to name a few. So this is where the hoppy bars come into play. We're able to gather data from that dynamic loading. And as I said before, the main assumption on these hoppy bars is that one-dimensional stress wave propagation. Now, what AFRL has tasked us to do is to integrate a striking mechanism into an already existing split Hopkinson pressure bar. Last year's design team was tasked to implement air bearings to reduce the friction in the loading. And since their main objective was the air bearings, their striking mechanism did not account for so much attention, and it introduced more than that one-dimensional stress wave propagation into the system. Also, their frequency response in their acquisition system was not fast enough to account for the dynamic loading time. Now, these are some of the initial sizing formulas. The first one we used to get a rough estimate of the size of our system. It relates the potential energy stored in a compressed gas, and it equals it to the kinetic energy in our striker bar. Second equation we used to refine our striker bar velocity once the system was in place. And then the third equation to my left of that second velocity equation relates the stress in the incident bar to the velocity of the striker bar. So since we are using a valve, the speed of the compressed gas after the valve will approach Mach 1. This will cause us to encounter a phenomenon known as choke flow. Now, choke flow means that no matter how much mass we put into our system, no matter how much pressure you put into our tank, we cannot pump more mass past a certain point through our barrel because we have compressed the gas to its full extent. So what we did was that we increased our diameter size.
So we designed our system around a set of requirements. These requirements for this system called for a system capable of storing potential energy. It had to release said energy instantaneously and create a consistent, measurable velocity, inducing a one-dimensional stress wave down the Hopkinson bar. Here we have a diagram of our stress imposing system. To the left is the capacitance reservoir, followed by the fast-acting solenoid ball valve, and our modified barrel for the striker bar. Here we have the striker bar. As previously mentioned, one of the design factors that had to had to account for in the design of the striker bar is an increase in bore size. By increasing the bore size, we would allow for a higher mass flow through the system, giving us a velocity that we wanted. So in increasing the bore size, we actually had a clearance between the striker bar and the bore. So we made up for that clearance with Delrin self-lubricating spacers, as you can see here. We went on to modifying the 1-inch barrel by incorporating an array of exhaust ports. These exhaust ports allow for expanding gases behind the striker bar to vent out into ambient, which will give us a constant velocity upon impact, which is also another requirement. Finally, our requirement for one-dimensional stress wave through the system was satisfied by really high tolerance barrel mounts produced by Professor Ziccarelli. These mounts ensure perfect alignment, well, as close as you can get, with the Hopkinson bar. We also took into account safety precautions when designing our system. Since we're dealing with such high PSI, we came up with backups. Here we have a safety release valve to ensure that our capacitance reservoir will never be overfilled above capacity. We also introduced an anchoring system which will be capable of holding such shocks and recoil during fires. Here we have the overall setup of the split Hopkinson bar and our stress imposing system integrated.
Okay, as we stated before, we're not only improving the striking system of the split Hopkinson bar, we're also improving the data acquisition. The data acquisition, which is the way we get results out of the system. The string gauges are the devices that we're using in order to read the change of voltage and the deformation on the bars. These string gauges, they have a metal foil inside that acts as a resistor in which electricity flows to it. If we introduce some displacement to the string gauge, that way the metal foil will create a tension, and that will create a higher resistance. And if we apply, if we move the string gauge the other way, we will be creating compression on it, and it will be creating a lower resistance. Every time the striker bar hits the incident bar, even though our eyes can perceive it, there is a deformation on the bar and a change of voltage. And it's also a stress wave traveling all the way through the bars, back and forward. In order to install the string gauges properly, the preparation of the surface is very important. The surface must be very clean, must be smooth with a very fine sandpaper, and it must be the oil with acetone. It must be degreased with acetone. And the string gauge must be glued immediately after cleaning, since any insignificant error can interfere in our results. These string gauges will pick up this change of voltage, will read the change of voltage, and it will be picked up by a Wheatstone bridge. Wheatstone bridge is an electrical circuit used to measure an unknown resistance. If we place 4 resistors of the same capacity, making a bridge the way shown in the picture, if we apply a voltage into the circuit, the voltage out will be equal to 0. So if we replace one of those resistors for a string gauge, we will be able to know the change of voltage that is flowing through that circuit. There are 3 types of setups for Wheatstone bridge. We have quarter bridge, half bridge, and full bridge. The difference between them is how many resistors you replace for string gauges. We choose to have a full bridge setup, since by having 4 string gauges, we will have a more precise reading on our change of voltage. Since our system is a very noisy system and the change of voltage is very minimum, it's very difficult to read that change of voltage and differentiate from the noise on the oscilloscope. For that, we're implementing a conditioner with an amplifier between the strain gauge and the oscilloscope.
The strain gauge conditioners are devices that will help us to complete the whistle-tone bridge. This strain gauge conditioner can complete the quarter bridge, half bridge, and full bridge setup. It amplifies the signal with a 5-volt excitation into the strain gauges. The amplification is adjustable, but in our cases we're only using 110 to 220 amplification because that's the frequency that only reads for dynamic loading. For the data acquisition, we're using a 2 gigahertz digital oscilloscope that is capable of recording up to 2,500 points per pulse. The resolution that we're going to use is 2 microseconds per point. For the velocity data acquisition, we're using a tachometer and remote optical sensors. This unit will be programmed in TCAP mode. What it means is single event capture mode. How it works is that knowing the distance between LED sensors, we program the unit that the first LED will trigger the timer on when the tracker bar passes through it, and the second LED will trigger the timer off. And in internal memory, we'll calculate the speed, and it will read in miles per hour. So this graph shows us the data that we're obtaining from the oscilloscope. As the stress wave propagates through the incident bar, in tension, it will enter the strain gauge, having a drop in voltage, and this strain wave, this pulse is equivalent to 2 times the length of the tracker bar. As it reaches the end of the incident bar, the wave will come back in compression as a reflected signal into the first strain gauge. And some of the stress pulse will go into the transmitter bar as a intention, as a strain data. Working this data, we're able to obtain the stress versus strain curve. Here are some of the formulas that will help us to achieve from voltage versus time to a stress versus a strain curve. In the first relationship, we are obtaining the strain using the voltage, output, the gauge factor, the Poisson ratio, and the voltage excitation in the system. Knowing this strain, we can go ahead and find the local displacement on the specimen, knowing the speed, sound of the bar, speed and steel, and the length of that specimen. But what we need is the engineering strain. So we need to integrate the local displacement and the strain in, we need to integrate the strain with respect to time so we can find the engineering strain. On the other hand, with the transmitter bar information, we need to find the stress on the specimen. This stress depends on the force multiplier that depends on the area of the bar and the area of the specimen. Since the area of the specimen changes instantaneously, it's difficult to know this, to determine the area, instantaneous area of the specimen. So we have assumed a constant volume relationship, and working out that formula, we came up with a final formula that the stress is related to the area of the bar, the strain of the transmitter bar, the initial size of the specimen multiplied by the engineering strain.
So overall, our project fortunately was funded by the AFRL in its entirety. We spent a bulk of our funds on the materials and the data acquisition system. So overall, our project was a success. We were able to implement a new striking system into a pre-existing Hopkinson bar that introduced one-dimensional stress wave propagations consistently down the system for readable data. And these are final questions.
Okay.
Any questions?
So I noticed you guys didn't have a result from a test that you all ran. Were you able to get your strain gauges?
We got the strain gauges working. We were
Okay.
not able to get any data from our oscilloscope.
Oh.
I believe it had to do with the signal conditioners that we were using. It was built, what we got, it seemed to resemble what we wanted, just the time scale was not there. And we were getting a lot of oscillations around the common origin, which signaled to us that it was the electronics filtering out the frequencies that we needed.
Do you anticipate any sort of issues with the conditioning of the initial impact point due to those Delrin collars on the striker bar?
Our advisor, Dr. House,
Uh-huh.
was not sure of this,
Okay.
but he told us to go ahead and try it
Yeah, I
out,
mean, you
and
gotta
we'll
do something,
find
right.
out from
Yeah.
there. But we put them about 1.5 inches back to minimize that effect as much as possible.
Just, could you come, there's something you have in your report, in the conclusion, I just want some clarification on it. When you talk about let me just quote what you have. They said the newly upgraded Hoppy bar produces a consistent and reproducible striker bar velocity up to 120 foot per second, right? Which finishes strain rates up to 104 inch per second. Is that what it is? The diagnostic system implemented upgraded the frequency response of all the components to 100 kilohertz. This minimum frequency required to interpret the data clearly without any distortion. Oscilloscope recordings is driven by the loading duration in the specimen. You said unknowingly the previous design team had problems viewing the characteristic square train waves due to the low frequency response of the data acquisition system. Could you just talk a little bit more about that? Could you explain?
In textbooks we've read that for a minimum you need 100 kilohertz data acquisition system. Now when you find the frequency of that, you're going to get about 8 microseconds time period per point. So our stress pulse turned out to be 83 microseconds. So the length of this square wave is 83 microseconds. If we were to use 100 kilohertz frequency time base, we would be able to get approximately 8 points in this square wave. Now using that, this oscillation effect is known as the Bow-Camber creep. It's the radial, it's the stress wave going radially in the bars, the ringing in the bars. So we have a stress pulse going down the bars axially, and as it goes down axially, it goes across radially as well. So that effect would be minimized if using 100 kilohertz time base. Now, the last year's team, they used a 4 kilohertz oscilloscope. That would come into play down here where you would not, or this one, you can't really see it too much, but you don't get more of the points. You get approximately 1 point every time the signal, the stress wave has transmitted and reflected back 3 or 4 times. So you don't get enough data to analyze the system. So you have to have a minimum frequency in order to get as much data and analyze the stress strain curves.
So you don't have enough data.
Yes.
What sort of strain rates are you guys measuring? Have you looked at it with your sample size?
No, we cannot. Because we didn't calculate that.
Okay, that's an easy answer. All right, that's it. Thanks very much.